welcome everyone. Good morning, good day and good evening. As Rachel said, what I'm going to present on is the development of materials to facilitate implementation of methods, presentation and statistical synthesis of data and not amenable to meta-analysis. This work has been done with a core team of people, myself, Simon Turner, Miranda Cumpston and Sue Brennan, who have been contributing to this project in various ways, some of which you'll see in the presentation today. And we're all based at the School of Public Health and Preventive Medicine at Monash University in Australia. So just to provide you a little context to the project, Cochrane commissioned 5 projects last year, which were about tackling methodological challenges in public health. And essentially what they were seeking was kind of practical tools to help the implementation of methods that are available in the Cochrane Handbook. And so this is just one of those projects, which is around obviously implementation of other synthesis methods. So before I begin, I thought I'd jump right in and get you thinking about the kind of ideas that I'm going to be talking in a bit more detail about. So here is a meta-analysis. It's fictional data, and what it's depicting is the effects, which are mean differences here, of pedometers versus no or minimal interventions on BMI. So we've got 5 studies contributing here. What you can see is that the authors of this review have made the decision not to synthesize the results, not to meta-analyze the results. So as a user of the review, if you come along to the study and you want to really answer the question of, are pedometers effective for reducing BMI? So what I'm going to get you to do is just look at this forest plot and have a think about what your response will be here, whether you think they are effective, whether they're probably effective, they're not effective, or you just don't know. And I'm going to get Rachel to bring the first poll up so that you can vote on what option you think is most appropriate.
Is the poll up okay, Jo?
Poll's up, perfect.
Okay.
So we've got 24 people. 19, that's probably everybody who's here, excluding the presenters. So, will you hear that poll, Rachel, or will I just read it out?
So yeah, if you just want to read out the results.
Okay, all right. So are pedometers effective for reducing BMI? We've got 1 of you said yes, they are. 6 have said probably. 5 have said no. And 9 said don't know. Okay, so we've got quite a range of responses there. So let's just move on to, we can share the results here. Okay, just so you can believe what I said is true. Okay, so what I'm going to do now is just move on to another question. So obviously you've come to a conclusion. Now I want to know how you came to that conclusion. So there are response options here are that you looked at the direction of the effects. You looked at the direction of the effects and their confidence intervals. You did something different to that, or you didn't know what to do. So if you can bring up the second poll, Rachel, that would be great.
Does that come up okay, Jo?
Yep, that's coming up fine.
Brilliant.
Thank you. Okay, so what we have here is, I'll stop the poll now and share the results. Hopefully you can see that. How did you come to your conclusion? Some of you one of you looked at the direction of the effects. 18 of you looked at the direction of the effects and the confidence intervals, and someone did something different. Just wondering if there would be anyone who'd be brave enough to tell me what they specifically did when they looked at the direction of the effects in their confidence intervals.
I can't see anybody with their hands up at the minute.
Am I allowed to randomly select?
Yeah, I think so. Oh, hang on, there is a hand up. Hold on. We've got Eugenie.
Yeah, I'll be brave. I said direction of effects and confidence intervals. Because although the direction of the effects seems to favour pedometers for most of the studies, except for MANSI, all of the confidence intervals cross the line of no effect and are also pretty wide. I guess you could suggest that the ITA Salo 2019 one has more weight, but again, that still crosses the line of no effect. So that's what I used for my assessment.
And so thank you for responding. That's great to hear that. And so if I can just push you a little bit more on that, if you were to kind of summarize, a bottom line summary, I guess, around how you would describe that, can you think about what you might say in a review, for example?
Well, I think if this was for like a grade outcome, not knowing anything about any of the other domains, because this is made up data, then I'd probably say that we can't be certain about the effects because the data is quite imprecise.
But would you try and quantify the result in any way? So, I think that you were saying one study looked like it was favouring the control, or studies that were favouring the interview.
I think that would depend, because you've said that you might not meta-analyse this, but not knowing anything about the studies themselves and how appropriate it is to actually meta-analyse, I guess there's a possibility if there was not a possibility of some sort of clinical heterogeneity that you could potentially look at these as a meta-analysis. But if you weren't, then you would have to use a different approach. So you would have to potentially look at them using something like SWIM and use a different approach to grade, for example.
Okay, thank you for that. Is there anyone else who wants to kind of add anything in for the approach they took there? Fine, if not, I think we'll move on. But I think that the point from this is really to see that that first of all, different conclusions have been made for the same set of data. And second of all, the approach that's used to come to those conclusions is differing. And so this really shows us that, there needs to be a focus on what the methodology is in this particular area. And this leads me on to some research that Miranda Cumpston, who's online today, is doing as part of her PhD, the research that she's leading. And what she looked at is a sample of 100 randomly selected systematic reviews of public health and health systems interventions. And what she found in that was that meta-analysis was commonly used. It was used in 58% of the reviews, but it was actually the case that other synthesis methods were also commonly used in those reviews, in 60% of those reviews. And in 27 of them, it was for some of the analyses, and for 33, it was for all of the analyses. So when we don't have meta-analysis, it's the case that other synthesis methods are commonly actually being used. But what the interesting thing about this study was that the other synthesis methods are actually really specified. In addition to this, there's also been other studies that have shown that between 35% and 56% of systematic reviews don't use meta-analysis at all. We know that then for a much larger percentage of reviews, it'll be the case that meta-analysis will be used, but it won't be including all the studies within it. There's lots of reasons for why meta-analysis is not used, but it can arise because of incomplete reporting of the effect estimates or different effect measures being used across the studies. And these are the kind of situations that the Cochrane Handbook, Chapter 12, which myself and Sue Brennan co-authored, we have put forward some other synthesis methods that can be used specifically for the situation where we've got incompleteness of different effect measures. So Chapter 9 of the handbook kind of sets out the array of synthesis methods that are possible in this table. And what we can see over here is we have what we call the kind of preferential or preferred methods, where we have meta-analysis, network meta-analysis, and so forth. But where we're not able to apply those methods, we need to consider other statistical synthesis methods, which are acceptable but don't provide us with quite as much information. And these include vote counting, combining p-values, and summary of effect estimates. And I'm going to show you a little bit more about this throughout this presentation. So it's the case that we've got new conduct guidance, which is available in the handbook. In addition to that, and in tandem with that, new reporting guidance for considering other synthesis methods was developed. That was the SWIM guideline, which was published in the BMJ, I think, around 2020. But also the PRISMA statement has been updated, and also really, in fact, in quite a lot more detail, tries to get authors to specify the methodology that they're using in their reviews. But it's the case that because these methods, the recognition of them, I guess, in some ways, is only much more recent, there aren't actually a whole lot of examples in the literature of people using those methods. And so this is partly the reason for this particular project, is to try and provide some examples that review authors, and particularly Cochrane review authors, can look at and think about how they might apply in their particular review. Okay, so the aims of our project were to develop 2 worked examples to demonstrate the application of presentation and other statistical synthesis methods. We want to apply those different methods to data in the reviews, provide example text for describing the methods and the results, and provide some computer code that helps review authors to be able to easily implement those methods. So what I'm going to do in today's plan is really to introduce the 2 worked examples. I'm going to introduce the kind of context of the review and illustrate some of the synthesis and visual display presentation methods that are used in these reviews. And then we'll have some time for discussion. So before I begin on the worked example, is there any questions at this point? Okay, I'll take silence as no. So this is this first example is what I've just shown you. Actually, it's a review that was looking, so it's fictional. It's looking at a review whose objective is to look at the effectiveness of pedometer interventions to reduce weight. In some ways, there's some simplicity to this review. So while it's kind of in the public health domain, they're restricted to including randomized trials, and they're looking at the effects of pedometers against alternative physical activity or no or minimal interventions. And I'm just going to consider the particular comparison here of pedometer versus no or minimal interventions. Let's suppose a range of outcomes are collected, body mass index, body weight, and then kind of cardiovascular type outcomes like blood pressure and so forth, and that the review is set in adults 16 years of age and older. So in some ways, quite a simple review, but when you're planning a review like this, of course, you always need to kind of think about the situation where it might be the case that you are able to meta-analyze a certain number of studies, but then there are going to be these leftover studies because the particular studies report the information incompletely, that you're not able to include them in the meta-analysis. So it's good to kind of plan for that particular situation. So here's some text that, for example, people could put in their protocol if they're thinking ahead about this particular situation. So we have our standard data synthesis section, and within that you might describe your meta-analysis methods, where you would be describing your model and your actual the meta-analysis method. But then you can also add in a section which highlights summary and other synthesis methods. So let's just kind of work our way through this. The first thing is that, and this is a kind of good practice for any review, we will tabulate available effect estimates, risk of bias assessments and population characteristics, and tables will be ordered by the risk of bias assessments. But we always want to kind of present the available information in a structured way, and a way that's helpful for interpretation whenever we do reviews. Then the next part of it is talking about what you might do in the situation where, for example, you're not able to meta-analyse all the studies. So while we make extensive efforts to include as many trials as possible in the meta-analysis, if we are unable to include most of the trials due to incomplete reporting of the results, we will supplement the meta-analysis with other synthesis methods. The synthesis methods we will consider using include meta-analysis of p-values and vote counting based on the direction of effect. We will accompany these synthesis methods with appropriate visual displays. And I'm going to delve into this a little bit more. So that's what you could do in setting up your protocol. And let's have a look at the data. So this is the data that's been extracted from the review. What you can see here is, so we've got the study name, the total sample size, risk of bias, and the median age of the participants in the trials. And what we've extracted out here is all the information that's available. And what you can see that these cells that are highlighted in blue here, they are the studies that can be readily included in a meta-analysis with no further assumptions. So the two kind of key ingredients we essentially need to do a meta-analysis are an estimate of the intervention effect and its standard error. So in this first example, a standard error is reported, and then for the mean difference here, where we've got in the second trial, we've got a confidence interval. From that, we can calculate a standard error. So these 5 studies could easily be included in the meta-analysis. But that's only 5 of 11 available studies, right? And in fact, it's also the case that these 5 studies only include 423 of the 1,500 participants who've contributed information to this particular question. So given that, this might trigger us in this review to think about using another synthesis method to supplement the meta-analysis. So in chapter 9 of the handbook, it's about preparing for synthesis. And one of the kind of first key steps in doing that is to actually think about what information is available to use for meta-analysis and for other synthesis methods. So first of all, you've got to say, well, here we've looked through, we can see that 5 studies can contribute to the meta-analysis. But if I was to use a different synthesis method, like combining p-values or vote counting based on the direction of effect, is it the case I'm actually going to have more information and more studies than I can include in those synthesis methods? So you have to kind of go through as a first step and see whether you've got that information. And what I've got up here is something called the standardized metric. You'll be very familiar with this in the case of meta-analysis. What we talk about is things like mean difference, standardized mean difference, odds ratio, risk ratio, and so forth. When we work with these other synthesis methods, we still have to calculate a standardized mean difference. It's just that what that is different to a meta-analysis. So if we're combining p-values, for example, then we're working our metric in this case is actually a one-sided p-value. And if we're looking at the direction of effect, then we just have a kind of binary value here, 1 meaning it's favouring the intervention, 0 meaning it's favouring the control. So looking across here, I'm not going to show you the details of how to get to these p-values. They're often reported in the publications. You can just extract them out. Sometimes you might have to calculate them. But what we can see is that if we look at the p-values, we're actually able to get 8 of the 11 trials. We're able to either directly extract or calculate a p-value. Now, associated with those 8 trials are 941 participants. So I've gone from 400 odd participants to 900 odd participants, and I'm now able to include 8 of 11 trials if I decide to use this combining p-values method as I've set up in my protocol. And if I decided to count based on the direction of effect, then I'm able to use 10, 11 trials to contribute to that synthesis, which would include 1,070 participants. So let's work our way through some of these synthesis methods. You're all very familiar with meta-analysis. Here we've got the forest plot. You saw that earlier on. a lot of you weren't convinced that there was an effect, but what we can see here is that when we combine across those studies, even although there's uncertainty in each of those studies, when we combine across them, it looks like there's some evidence that wearing pedometers reduces BMI. Whether that's an important difference or not is another question, but there's some evidence that there is a shift in BMI. So that's our first synthesis method, but it's only including a fraction of the data. So we might consider from our protocol that we're going to actually meta-analyze the p-values. Now, what question does that answer? Well, it answers a different question to a meta-analysis. A meta-analysis gives us an estimate of an average effect and our certainty around that effect. What a meta-analysis of p-values answers is the question of, is there any evidence that there's an effect in at least one study, right? Quite a simple question it's answering. The method that's I've outlined here is the Fisher's method for meta-analyzing p-values. I'm not going to talk through that in detail, but what I want to show you is that it actually can be quite easily implemented in software packages. So here it is in Excel. Basically, this is our p-values, and this code that's in these formula that are in these cells here are just implementing this. And what we get from this is a p-value, which tells us, in this case, that there's strong evidence, because that p-value is very small, there's strong evidence that there is an effect, that pedometers are effective in at least one of the included studies. And this is just the same again, but I've implemented this in the statistical package starter this time, and you can see that's exactly the same p-value that's been calculated there. Now, there's a companion plot that's a very helpful plot that goes along in some ways with combining p-values. So this is known as the Albatross Plot for obvious reasons. I've heard someone, actually Sue today, called it the sprinkler plot. So take your pick as to which you prefer. But what the Albatross Plot allows us to do is to get approximate estimates of the underlying intervention effects. So here we've got these dots. These dots represent each of the studies. And for each of the studies, what we've got information on is, if we've just got information on the number of participants and the p-value, the exact p-value, we can plot that on this plot here. And what we can do is we're actually able to superimpose on this plot these contours which represent different standardized mean differences. So here we've got standardized mean difference of plus or minus 0.5. Here we've got 0.25, and here we've got 0.1. So a standardized mean difference of 0.1 is pretty small. 0.25, still pretty small. And by the time you get into 0.5, it's starting to be a bit more of a moderate effect. So what we can look at here is where these points sit, but between these two contours tells us something about the magnitude of the effects in terms of standardized mean differences. So what you can see is we've got these circles here. These are the that are not colored in. These are the 5 studies that contributed to the meta-analysis, although now I'm looking at standardized mean differences, not mean differences. And what you can see is that these black dots here are the studies, the 3 studies that I couldn't include in the meta-analysis because there was not enough information reported, but I'm able to include on this plot because those studies reported number of participants and a p-value. And I can see that they are generally in the same direction. So they're all saying that actually that pedometers are favourable for reducing BMI. And in fact, they are quite kind of consistent. So you can see that these 2 dots here are showing that the standardized mean difference is likely to be somewhere between 0.1 and 0.25. It's only that we've got this point here. The study is showing a much larger standardized mean difference than the other 5 studies that are included in the meta-analysis. But you can see that this actually provides us with quite a lot of information. And then the final synthesis method that we cover off in the handbook and also in these worked examples is really vote counting based on the direction of effect. And what this does is it allows us to answer the question of, is there any evidence of an effect? So what we do is we categorize each effect as showing benefit or harm based on the direction alone. So you can see in this column here, I know for the first study, there's a reduction in BMI. So I've coded my directional effect as 1. Down here, I can see my mean difference is 0.4. So actually, in that case, the no or minimal intervention group is beneficial. So I put a 0 here. So I basically categorize each of these. Then I count the number of effects showing benefit and the number showing harm. And I can also accompany this with a hypothesis test of testing whether the true proportion of effects favouring the intervention is equal to 0.5. Because that should be the case. If our intervention is not effective, then just by chance, sometimes a study will show that the intervention is favourable. Sometimes it will show it's harmful. But, you know, if we were to repeat that multiple times, our estimate of the proportion of times the intervention was beneficial would be 0.5. And we can also calculate this proportion and calculate a confidence interval for it. I'm just going to say a note here. I haven't got a lot of time to really talk this through, but we don't do vote counting incorporating statistical significance. And the main reason for that is if we've got small studies, even although they might show a small underlying, they might have a small underlying true intervention effect, those small studies will always count towards the null because they don't have the power to ever reject the null hypothesis. They're not large enough. And so we can end up with very incorrect conclusions when we base our count on statistical significance. Okay, so what we can do, here's just an example in Starter. We can do a test, doing this binomial test, testing whether the proportion of interventions are favourable. The proportion of studies favouring the intervention is equal to 0.5, and what we get here is a p-value of 0.10. So there's no indication that the intervention is favourable using this particular vote counting based on directional effect. And when we look at the confidence interval, you can see it includes 0.5. Now, the reason, in some ways you might say, well, what's happening here is our vote count test is kind of in disagreement with our meta-analysis and our meta-analysis of p-values. The main reason for that here is really when you do vote counting, you lose an awful lot of power. You know, we're bringing down all the information we have to basically 10 values of 1 or 0. So we're throwing out a whole lot of information when we get to the point of vote counting. And so we end up often not with enough power to detect an effect, even although one might exist. Okay, so how might we write this up? Here's an example, just considering meta-analysis of the effect estimates and also a meta-analysis of the p-values. So 11 trials with 1,500 participants examined the effects of pedometers compared to no or minimal intervention on BMI. 5 trials could be included in a meta-analysis, which showed a reduction of minus 1.13 BMI units. Meta-analysis of p-values, including 8 trials, 941 participants, provided strong evidence of the benefit of pedometers. The 3 additional trials included in the meta-analysis of p-values yielded consistent results to the trials included in the meta-analysis, indicating that pedometers were beneficial. Exclusion of these 3 trials from the meta-analysis is unlikely to materially affect our interpretation. Okay, so that's the end of the first worked example. Are there any questions at this point? Okay, I'll move on to the second example. So this second example is actually a review that's on the library. This is looking at interventions to reduce ambient particulate matter of air pollution and their effects on health. And what you'll notice here, this is quite a different scenario to the one I just showed you. This is the logic model for this review. And what they're looking at is a whole series of interventions to reduce air pollution. In particular, I'm just going to focus on the vehicle interventions. And what's interesting here is that the vehicle interventions, even when you just look at those, there is a whole multitude, multi-component, lots of different interventions. So, it's a very complex scenario. Over this side, we've got outcomes, there's health outcomes and there's non-health outcomes, and we've got ambient air quality. So we've got a whole lot of different indicators of air pollutants here. And I'm going to focus on these in this presentation. Eligible study designs, again, we have a much more complex situation than the previous example where it was only randomized trials. Here, it's all sorts of studies that we have, lots of observational studies. We've got randomized trials. In this particular scenario, we tend to have cluster randomized trials. There are control before or after studies, interrupted time series, so on and so forth. So we've got a much more complex situation to deal with here. So just looking at what they did in the review, in terms of measures of treatment effect, they had said that initially they aimed to use mean differences in risk ratios, but the observed effects reported by the main studies were very heterogeneous and due to varying analytical methods and reporting practices. So here we've got the problem of different effect metrics potentially being used across the studies, and also probably incomplete reporting where we might have information on effect estimates but not precision reported. Also, another particular issue that's likely to arise here is that these studies tend to often look at pollution over time, and we have correlation over time, and some of the studies might not adjust for that. So we might have standard errors, but those standard errors could be incorrect. So thus we extracted any measure of intervention effectiveness reported in the main studies, which reported an association between the interventions and outcomes. And then they wrote in about the evidence synthesis. As the evidence proved too heterogeneous to conduct meta-analysis in line with the review protocol, we synthesized evidence narratively as well as graphically using harvest plots. And I'm not going to talk too much about those because we're going to speak to those in a bit more detail shortly. So that was their main approach. And when we get to the results of the review, they've got this nice descriptive tables that kind of, talk through or provide information about each of the interventions. So here we've got vehicular sources, vehicular interventions, and we've got subcategories within there, the type of intervention, along with the description. The review was structured by comparison. So there were lots of, as I said, lots of interventions, industrial interventions, vehicle interventions. So it was separated by comparison. And within that, outcome groups. So there were health outcomes reported first, and then ambient air quality outcomes. And then there was an individual reporting of results. Each section began with a summary of the evidence. So here is an example where we're looking at the vehicular interventions. You can see that we've got, we've got figures 11 and 12 observed associations between interventions to reduce ambient air pollution. Sources in both health and air quality outcomes were mixed, with most studies observing either no clear association, either direction or a significant association in favour of the intervention. So there's this kind of summary statement provided at the start of each of the comparison sections. And then each of the, they present these harvest plots. I'm going to let Simon talk in a little bit more detail about that shortly. And after they've given that kind of introductory statement about their summary of the evidence, they provide the results from each single study. So we've got this Bogard study, and they provide the information on PM10, 11% reduction in intervention sites, 14.7 at control sites. And this just, they talk through each study by study. And they also provide in the appendix basically the information that they could extract in a structured way for each of the outcomes and then the interventions. So what else could they have done in this review? What are the other kind of possible options that we could apply here? Well, one thing that we could do is it's always incredibly helpful to use structured reporting. So we've taken some of the data that they had in this review. Similarly to what they did, we've ordered, so we just got this table here, we've ordered by comparison an outcome, which was as was originally done, but we've also ordered by risk of bias assessment to increase the prominence of the most trustworthy evidence. So say, for example, we look at the NO2 here, we can see that the studies which are at least risk of bias, they are, and they're using not the Cochrane risk of bias tool here, you can see that they are highlighted as the first studies that you view when you're looking at this particular comparison and outcome. We've also included the study design here, so the kind of methodological features that might potentially compromise your trust in the findings. And we've provided the standardized effect. So here, essentially, what they are doing in this review is basically vote counting. And so we really want to be able to say for each study and outcome and within a comparison, did the study favour the intervention or did it favour the control? So this is almost like, well, it's exactly like presenting our actual effect estimate if we were to meta-analyse the results. So here we've got favours intervention control. Very clear when you look at the data to see where that comes from. So the presentation of the standardised effect really essentially here aids in the transparency, and it's akin to reporting effect estimates for meta-analysis. So that's what we can do in terms of structured reporting. And I'm going to hand over to Simon now because he's going to talk through the traditional harvest plot and his modification. Thanks, Simon.
Thanks, Jo. Yeah, as Jo was saying, in the previous table, we sort of had a setup nicely that showed all of the different effects and whether they favoured control. And traditionally, you see these sort of harvest plots that are vote counting methods. And we've made this slight modification to the one that we saw from the actual paper by removing the column in the middle that was the one that showed no statistical significance for the reasons Jo talked about before. And also chapter 12 of the handbook is really fantastic at setting out all of these reasons in more detail. But in this harvest plot, what we're looking at is on the left-hand side, we have studies that favour the intervention, and on the right-hand side, those that favoured control. Each row is a different outcome, and each bar is representing the result from a single study. Now here, they've tried to emphasise the low risk of bias by making the bars higher for the low risk of bias ones, down to the small bars, which are for the high risk of bias. Now that sometimes a bit confusing. And if we go to the next slide, Jo, we've got this is a reworking. We've had a look at the harvest plot and are trying to make it a little bit more accessible and readable. And so here we've got the vote counts again, and you can see there's multiple plots there, one for each of the outcomes. Now, this is quite efficient in terms of space. You can see that you can get a nice compact view of it here. Underneath, you can see that we've got the old harvest plot, which takes quite a lot of space. Now, I've stacked them vertically here because when we stack them vertically, it's very quick. It's very efficient to see which, whether intervention or control have more studies on the side. If we look at that first one there, we've got 6 studies that favour intervention, 5 studies that favour control. I've used different colours and symbols for risk of bias here. So you, and with the foundation, the studies at the bottom being at the lowest risk of bias. Now, again, we're ignoring statistical significance here and are just looking at the direction of effect. And we could shade them. In this case, I've shaded because in the original we had different types of study design, controlled before and after designs and interrupted time series designs. And so this is just a way of seeing all of that information in a nice compact form that you can scan your eye across and see. Now, on the next slide, I've sort of highlighted that because we've put the low risk of bias down the bottom, if you're keen to see just what the low risk of bias studies bring to the study, it's very, very easy to scan your eye across. And if we have a look at the nitrous oxide, the NO and the NO2 column right in the middle there, you can see that there's lots that favour the intervention, but actually there's just 3 that are the low risk of bias. And although there's fewer studies that favour control, there's far more studies on that side that have the low risk of bias. So I think this is a type of plot that could be useful. You can stack them this way if you desire. Some people prefer to read down the page for each of the different outcomes. And on the next slide, we can see, as Jo was talking earlier about the p-values, we've got a table on the next slide, Jo, I think that's got the vote counting on direction of effect by outcome. Now, Joe's already showed a little bit about how we can do this for one outcome, and in this particular review, there were multiple outcomes, and it would be very helpful to set this information up in a table. I think having structured tables is very helpful. And as Joe showed before, you can do these calculations in Excel or in any statistical package as well. Now, here we've restricted to looking at only outcomes that have enough studies for it to be reasonable to even have an estimate of this proportion. And we can see here from the vote counting based on the direction of effect by outcome, the p-values are quite high there. And finally, sometimes you do have enough information to get the actual values of the outcome, whether it be a standardized mean difference or a mean difference or something like that. And it's quite useful to be able to still look at where these are and get some sort of information about the risk of bias. Now, in the handbook, we strongly recommend that if you've got this sort of information, and a box plot is quite useful, or a dot plot that shows the actual values for each study. And here we've just combined the two together. So we've got the information, the combined information there on the left, that's all of the studies that have contributed. And then we can split by different outcome groups. And again, by showing the risk of bias assessment, that's the colors again, we can actually see some interesting information in this diagram that might not come up in a traditional sense. We've got the green ones, which is the low risk of bias, all sit quite down low. They have the low values for the outcomes. The high risk of bias ones are the ones that are further up to the top. So using these sorts of plots, I think, is very useful both for presenting the information for the reader and also, I think, as an overview when you come to perhaps write up the results or what you want to talk about. You can use this to help inform your decision making and how you might try and express those results.
Thanks, Simon. So I'll wrap up then. So in terms of the document that we are writing, which is being finalised internally and is very close to completion, what it's going to include is the introduction to these two examples, example text for the methods of the review in terms of the protocol and the review, and also kind of suggested text around the results of the review. Now, these are just examples, so they're not prescriptive in that people would obviously have to follow them and they need to kind of think in a particular scenario whether, you know, how the conclusions work for that, the particular results that they obtain. There's the illustration of the different synthesis methods. We have code in there to implement them in various packages, and Simon's written code to implement harvest plots, those modified harvest plots that you've seen, box and whisker plots and dot plots in R. So that's all freely available, will be made freely available. Once our document's finalised internally, we'll be seeking feedback from our advisory team, and then that will go out for review authors to use.